Expressing solution steps. I want to take you on a thought experiment. Ready? Tell me the steps to register on our website for membership. Stop right now. Go to our website, get out a piece of paper, and write this down. What are the steps to register for membership on our website? When you're ready, start the video again. All right, let's go through the steps to join. Ready? I'm sure that you probably wrote these down. Here we go. Step 1, click on the Join button. Step 2, fill out the form. Step 3, then activate your account. Now look at the steps that we just wrote out and answer this question. Could your grandmother follow these steps, 1, 2, 3, and then successfully register for an account without asking for your help? Could she do that? Think about it. Are these steps so explicit that even your elderly grandmother could walk through them without even asking for your help? And could she successfully register? Shake your head no, side to side no. The steps are missing, right? It needs more detail. So what are the problems here? We have 1, 2, 3 steps. What if you're not on the home page? Where is the Join button at? What do you put in the form, and where do I add that? How does my information get into the computer? How do I activate my account? What does that even mean? A computer needs exact, explicit steps and conditions to be able to perform its task. We've already discussed that. So therefore, let's go through another thought experiment, and I'm going to help to drive this concept home for you. How do you compute 149 plus 537? How do you compute that? I know, you went and grabbed your calculator, didn't you? Yeah. Okay, well then let me reframe that question. Here we go. How does your calculator compute the answer? So you're typing in 149 plus 537 equals, and do you think that the calculator just runs that in its circuitry and it magically knows the answer? No. There's a piece of software in there. Yeah. There's some circuitry and there's a little piece of embedded software that actually runs through the adder circuitry. And it does what the process that we're just going to go through here. So it takes the inputs, those numbers, and then it adds those numbers together. Well, how do we do that? So think about that. How do you add 149 plus 537? So I'm going to take you over to my whiteboard. Here we go. So welcome to my whiteboard. Get used to this whiteboard. We're going to use it a lot so I can help you to visualize these concepts. It's a way of you and I being able to communicate with one another. So here we go. We want to add 149 plus 537. And you know, back in grammar school, you set up your calculation like this, correct? You laid them on top of one another and lined up the columns, although I didn't do the best job in lining these up here on the board. And we learned back in CS 100 that this is base 10, right? And what we do is we add together the individual columns, which have digits in them. So let's just talk about digits here real quick. Let's get our terminology down. So a digit. In base 10, what are our digits? They are 0 to 9, correct? And you put these digits together and you get numbers. And these become our counting numbers that we use in our natural system. They're also our integers. All right, so let's take a look, and we're going to go and let's just recap positional notation. So here I have all these lovely little positions. And if I go and I put a 9, a 4, and a 1 in each of these boxes, we can say this is 10 to the 0, this is 10 to the 1, this is 10 to 2. The 10 to 0 means that I take this digit of 9 and I take that times 1, correct? And that gives me 9. I take this 4 times 10. That gives me 40. I take this 1 times 100, and that gives me what? 100. And then I add those together, and that gives me the 149 in base 10. So these digits and how we add numbers together, we go by the columns, column by column by column. So therefore, we've lined up our columns. All right. Now, your job here today is to actually write each of these steps out. And you want to write them out in such a way that I can add any numbers together. Any of these integers I could add together. All right, so let's do that now. Here we go. So I'm going to go and I'm going to put, what's the first step? What do I do? Well, let's just do it, and then we'll capture what the steps are over here. So I'm going to start right here, correct? I'm going to start in the rightmost column, and I'm going to add 9 plus 7. And what is that? That's 16. So let's put our 16 right there. And what is 16 comprised of? We're going to go this way. We're going to capture that, and then we're going to write these steps down. 16 is comprised of, well, let's just do it again. Make sure that you're understanding. Here are each of our columns, right? So this would be the tens column. This is the ones column. So if I put a 1 and a 6 in there, then I can see that, oh, this is the tens column. Okay. The 4 and the 3 are also sitting in the tens column. And the 6, which is the least significant digit, that's the 6, is the ones column. All right, so then I have 10 plus 6, that gives me 16. So what do I want to do here? I want to take the 6, because that's the ones, and I want to leave it in that column. And then I want to carry this 1 because it's in the tens column, and I want to carry that up there. All right, so let's go ahead and capture the first parts, and then we'll go back and we'll capture this. So what's the first thing that we did? We added the digits together, right? So let's go, and we're going to say add. So we've got add the digits from the rightmost column together, right? And that's the least significant digit. That's the LSD that I put there. What's the next step? Well, obviously we need to save that sum. I know that seems intuitive, but here when we do it, we actually add these together and then we write down the sum, which is 16. So here we're just going to call it as save. So obviously a computer's not going to write it down. Instead, it's going to save it somewhere in a register, in memory. All right, so what's the next step? So we wrote down the 16, we've saved it, right? So that's this step right there. And the next thing that we said was, okay, now I need to split this out and determine if I have a carry. This would be our carry number, our carry bit. Remember that back from the full adder in CS100 that we have a carry bit here. Right, okay. It needs to go into the next column. It doesn't belong in this column. So therefore, let's go ahead and write that step down. So let's say, what do? We want to write down this 16 and capture it in that column. Now, we could write it as this. Write down the 6 in the ones column. We could write it like that, couldn't we? It's very specific for this one particular implementation. What if I want to add together 52 plus, 5? What if I want to add that together? This wouldn't work anymore, would it? No, it wouldn't. So therefore, you want to start to think, even though you're writing specific instructions, you want to start to not have them so linked in with the specific implementation, which is just that this set of instructions only works when you're adding these numbers together. No, you want it to be much more general, but still specific to solve any set of problems. So you're going to hear me use the word, we want to decouple our solutions that we're writing here from the actual implementation, but yet come up with this recipe, this set of instructions, the step-by-step explicit step of instructions for adding numbers together. That's what we're really trying to do here, right? You're trying to write a program. You don't want it to just be a one-time program. Well, I can only use it for just this specific thing. That's it. I can't use it for anything else. No, that's kind of wasteful, isn't it? Plus, we'd have a lot of steps here. As you're going to see, we're going to be able to reuse these steps and come back around and do it again and do it again. We want to be able to loop through these steps. So start to think about it in that way. So let's rewrite this. What would our step here be? So all that we want to do is capture that position and put it here in this column. So why don't we say this? Place the sum's least significant digit into the column. This is the least significant digit, isn't it? And the 1 is the most significant digit. So just by doing this, you could say place, you could say save. It's the same thing here for what we're trying to write. So right now, we're just verbalizing. We're trying to capture these steps in this written form. By doing this, we can see that, okay, so I follow this and I say, yeah, all right, what is my least significant digit? Well, it's a 6. All right, so I place that in that column. So let's do that now. I'm going to get rid of this. Here we go. I'm going to put that 6 right there in the ones column. Well, I've still got the 10s, right? Because that's 16. So what do I do with that? So think about this. When would we have a carry bit? If the sum, see, we save the sum up here. If that's greater than 9, that's right. I'm going to have a carry bit. So therefore, I can say, then carry the remaining digit to the next column. All right, let's go ahead and do that. There, we just carried that to the next column. So then, what would be our next step? Number 5. What if I got down here and I'm adding just this column? Remember, we want to be able to loop through this. Hold on to that word, loop. Come back around and run this again. Or I'm adding 1 plus 5. That's it. That's all I'm adding. So there is no other column. Instead, I just have a 6 here. Well, that's kind of funny. These are both 6. That wasn't intentional. What would be my next step? I need to determine if I need to be adding another column. Is there anything else in that next column? So therefore, let's do an if. That's how we would think about it, right? In our own mind, we would say if the next column is what? Greater than 0? If there are digits to add together. So if there are more digits to add in the next column, then we're going to move to the next column. Otherwise, we'll just stop. And we display the number because that's the answer. So let's try that now. Let's say if the next column is greater than 0, meaning there are digits to add. So you could say here, why did I say greater than 0? 0, 0, 0, 0, 0, 6 is still just 6. It's 6 ones, right? So therefore, it can be 0. So if you think about it that way, then yeah, the next column is greater than 0, meaning there are digits left to add. So let's think about it from a circuit point of view. Remember back in CS 100, if I have my full adder, this is my outputs. I have 2 outputs. That's my sum. It's going to be a 1 or a 0, and that's it. And then my carry out, which will be a 1 or a 0. But then I have these inputs coming in. When there's nothing there, there's nothing left to add, there's a 0. So therefore, by saying if the next column is greater than 0, then, yep, that tells me, it infers that there's more digits to add. Then, do something. What are we going to do? We're going to move to that next column. So we're going to, in circuitry, move to the next full adder. Move to the next column. Okay. Well, this is an if. Is there an else? Yeah, we already talked about there's an otherwise with this. So in software terms, we would say if this, else that. It's our natural way of communicating. So if I'm going to go do this, I would do this if these conditions are just right, or else I'm going to go and do something else. So let's go ahead and we'll put else here. So notice I've got an if, I've got a then, just kind of highlighting these, getting these into your mind. We're going to talk about these later on, but I just want to get them into your mind. Else, what are we going to do? We're going to stop. I combined two things here. This really would be two separate steps, but I'm just going to go ahead and put this down and then display the sum or the number, because that's the answer. This is really two separate steps, but for now, I just want you to see that, else we're just going to stop. All right, well, let's say it's not an else. Let's say we're back over here with ours, and I'm going to clean up the board. All right, so we've moved our pointer over. Now I've got a 1, a 4, and a 3 that I have to add together. So what's the next step? Well, let's look at our board. Could I come back up here to step 1? Could I say add the digits from the rightmost column? No, I couldn't, because that would take me back over here to the 1s. So I can't do that. So I need one more step down here. So I'm going to have to say 6, add the digits. All right, so I would add the digits. 1 plus 4 plus 3 is what? That's an 8. All right, what's my next step? What can I do? Hey, I need to save the sum. Well, I've got that right here on step 2, don't I? All right, and then I place the sums LSD into the column. Well, I just did that. So, okay, that one works. Yep, that one works. This one works. How about this one? If the sum is greater than 9, no, it's not. All right, else. Well, there's no else here for this one. So therefore, I can just skip this. That's telling me that, yep, it's only an if, do that. Otherwise, just move on. I just don't execute this step number 4. All right, so what's step number 5? If the next column is greater than 0, so there are digits to add. Yep, I still have digits to add. Then move to the next column, else stop. So I can do all of these steps, can't I? So let's go ahead and we're going to do that. We're going to say, go to step 2. You need to be specific. Where are you telling the program to go to? So we're going to come back here. We just created a loop. Yep, we changed our program, didn't we? If you're visualizing in your mind, if I'm writing this up, if I'm telling a person steps of how to solve adding two numbers together, I would go and I would say this, and I'm starting to execute and I'm coming down, and then I say, oh, well, wait, instead of just writing this out and having all of these individual steps to add this specific implementation, we made it general enough and it's decoupled. We're going to talk about decoupling later on. I just want to present it here to you. The idea of general, decoupled, but it's still explicit, right? It still explicitly tells you what to do. It's just in a general, reusable, decoupled format. Hang on to these ideas in your mind. They're very, very important in software development. You'll hear me harp on them. So let's go ahead, clean this up. And let's see if this works all the way through. Ready? So where are we at? We got to the 8 and we said, okay, come back up here and save the sum. All right, well, we did. Place the LSD, the sum's LSD into the column, and we did that. If the sum is greater than 9, nope, it's not, so we can skip that step. If the next column is greater than 0, yep, I have that. Then move to the next column. All right, I'm moving over here. Now I'm in the third column. Step 6, add the digits. All right, well, I've got 1 plus 5. That's 6. All right, add the digits. All right, I did that. Go to step 2. Let's come back up. Save the sum. Place the sum's LSD into the column. I did that. If the sum is greater than 9, nope, it's not. Skip that. If the next column, oh, wait, I don't have a next column. All right, so no, it's not greater than 0. Let's go do the else. Else stop and display the sum. On your calculator screen, you would see displayed 686, right? That's what you'd see displayed on the screen. This is how your calculator would solve that problem. However, your calculator would also have another piece of software in there, or it's combined in the same circuit that actually tells us, load this number into the register, load this into here, pull this into memory, now store that away in memory. It has more specific steps to it. For us, we're working at a higher level language. There's other pieces of software sitting below, so it takes our steps here, these steps we just laid out, 1 through 7, and it then breaks that down, and it handles, when I say save the sum, it's handling that for me. So here I'm also assuming that these numbers are already been fed into the circuit. So I did not say input. I didn't say capture. I didn't say input. Instead, I'm just loading it right into memory and I'm saying add these numbers. All right. I want you to spend a little bit of time. Stay right here. I know this seems very elementary, but it's not. Coming up with this type of concept is the basis of how you will write programs. It's the basis of how you're going to visualize in your mind how you just solve such a simplistic problem of adding two numbers together. I hope that you can appreciate what we just did here. We took a problem and then we wrote down a way to visualize that problem, right? So here is our visualizing the problem. And then we converted that into a written step-by-step explanation of how to solve that problem. Okay, cool. So let's just recap here. What did you just do? You wrote an expression of how to add two positive integers together, didn't you? That's what you just did with me. We walked through that process, you and I together, and you expressed. Going to keep emphasizing and harping on that expression. I think it's very important that you understand that you're giving a problem set and you're expressing it first visually. You wrote it out then in these instructions. It was very verbose, wasn't it? It was intentional. We're trying to break down a problem into solvable steps. So let's just walk through and recap. So we have an expression to add two positive integer numbers together. We added the digits in the rightmost column. We saved the sum. We placed the sum's LSD into the column. If the sum is greater than 9, then carry the remaining digit to the next column, all right, because that's our carry bit. And if the column is greater than 0, that means then I have more digits to add, right? Then move to the next column. Otherwise, we're going to stop and display the number. We do have more digits to add, so therefore step 6, we said add the digits. And step 7, we said, hey, go ahead and go back. Let's reuse this program. Oh, cool. Go back to step 2 and do this again until you get to the else. So let's just continue looping here, right? It's just going to keep going down these steps and loop and come back down. And here's a conditional. Here's a reason why you might jump out of this loop. So you're just sitting here forever, looping, 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 adding, until we hit this else. Nope, there aren't any more digits to add. So go ahead and stop. Let's break down the expression's key attributes. This is very important. Ready? Make sure you pay attention. It's explicit. It's step by step. It's repeatable. It's absolute. And what do I mean by that? What do I mean by explicit, step-by-step, repeatable, and definitely what does this absolute mean? It means that I can take any set of numbers, the 613 plus 21, 98,045 plus 3,270, or just simply 0 plus 1. I can take those and I can add them together, and I can always get the same answer. So why? So that any person or device running the sequence that you just wrote will arrive at the same result or behavior. I wrote down behavior on purpose. We're not always just adding numbers together. Sometimes we get a behavior out of something that we're doing. Storing data, sending that data to the database. It's pulling data from a file. It's pulling data off of a screen. It's outputting data. It has a behavior. It needs to be Remember the points. Go back. What were the points again? Explicit, step-by-step, repeatable, absolute. Notice I didn't say specific. I decoupled myself. Don't want it to be a specific implementation. Instead, I only need those 4 earmarks, and that's it. Congratulations, you just learned what an algorithm is. There's one of those big, scary words. You hear algorithm all the time, don't you? Yeah, if you're reading articles out there from the software development world and software engineering, computer science, we talk in algorithms. And there are a lot of algorithms. You're developing algorithms. When you write code, if it meets those 4 earmarks, you're writing an algorithm. It's a recipe. It's a set of instructions. We'll have a whole course, actually probably a series of courses just on algorithms. Going into those specifics are outside the scope of this particular course. But here, I just wanted to introduce you to the word and the concept behind the word, because it's very critical to computation. It's a big part of what you're doing. So what are our takeaways? Software tells the calculator, which is a computer, how to solve the problem. The solution is expressed in a language that is explicit, step-by-step, repeatable, and absolute. If you're going to take something away from this course, write those 4 things down and pin them up on your wall, stick them to your monitor, and make sure that when you're solving problems, they're explicit, step-by-step, repeatable, and absolute. Then you can reuse that solution over and over and over and over again. An algorithm, it's just a recipe. That's it. Which is meeting those attributes we just talked about. It's explicit, step-by-step, repeatable, and absolute. It's a set of instructions. It's a recipe. That's it. It's that big, scary word. You've learned it. So now if you're on a code interview and someone asks you what an algorithm is, you know what it is, don't you? You may not know all the specific algorithms that are out there in the world. You're going to learn those later in future courses.